Looks great.
You're all set.
Thank you. Let's see.
But I think there's a loose connection.
Okay,
I
hopefully.
think there is a loose connection.
A loose connection?
Yeah.
Okay. You guys.
Don't be sorry. It's not your.
Okay.
Oh, it doesn't work.
No, that's it's just
Screen mirroring.
Okay. Everything is operational. Take it away. Oh, actually. All right. Oof. Okay, thank you guys for making it over here. We are very excited to have Roitaro Okabe coming from MIT. He is a PhD candidate in chemistry at MIT and earned his Bachelor's of Engineering and Master's of Engineering from the Institutes of Science Tokyo. His research interests include the computation-based study of the structure-property relationships of complex systems. He applies his networks for property prediction and designs material candidates using diffusion models. Beyond his doctoral work, he has conducted research internships at IBM, Thomas J. Watson Research Center, as well as prior internships at Yale University and Rice University. And today he's going to be talking about advancing quantum material discovery with geometric machine learning. So without further ado, take it away.
Okay, so let me start. Hi everyone, thank you so much for attending today's seminar. I'm Ryotaro, a current fifth year PhD student working with Professor Minda Lee. Today I want to talk about our research progress called Advancing Quantum Material Discovery with Geometric Machine Learning. Like in this presentation, I would like to highlight mostly about the two papers shown here. Want to start from the brief the introduction background of our motivation. We are interested in defining this material candidate. Material design is not at the heart of the modern technology. All the material come from this finite number of the element on this periodic table. However, there can be quite a huge combination that provide different functionalities, such as battery, solar cell, carbon capture from the metal organic framework, which we heard the great news this morning, and also quantum computers. To design and realize the target material in the real world, we need to consider in the broad perspective. Of course, we need to consider the target functionality, what kind of the property do you have, and also stability, realizability in the real world. Besides that, we need to consider still the multiple factors. For example, we need to consider whether the material can be synthesized by the experiment, and also whether this material production or material cell has some environmental impact. For example, our recent work showed that the more the quantum the material is and the more the toxic that they can be. And to balance the multiple factors, we aim to develop the machine learning to discover the function material for the real application. And to find out the material with the desired functionalities, it's quite essential to identify the physical properties of the material in an efficient way. For example, the thermal properties of material, such as the heat capacity or the thermal conductivities, it's quite important for handling the limited energy sources. To identify material with the desired properties in each scenario, we study the lattice vibration, which gives the rise to the phonon related to the carrier of the thermal energy. Traditional experimental approaches using the neutral scattering demand extensive resources and time, as well as the facilities very quite limited in the world. Or in the similar way, the theoretical calculations often burden the researcher with the computational complexities. Considering the hundreds of the thousands of the known material in database like the material project, it's not realistic to screen all the material or large part of the material candidate with the existing techniques. However, the advent of the machine learning, especially with the one with graph neural network, has opened this transformative revolution. GNN-based models stand as a game-changing solution that can efficiently predict this material physical properties with higher speed, and also this cutting-edge technique can provide this further material screening that can lead to the discovery and the design of the new material. So it's essential to develop this material how to prediction of this material property given the material structure. Besides identifying the properties of existing material, there are also challenges in exploring the new materials. Actually, the design space of the material, it means that combination of the atomic species and position, etc., is quite enormous. Even today, it's believed that only a small fraction of the realizable materials has actually been discovered. Traditional approaches they rely on starting from the huge material candidate that we can usually take from the material database, and then filter down using the heuristic and the high throughput the property prediction. That is the mainstream way. However, this process is like the discovering the diamond under deep in the desert. It's not efficient because even studying from the large candidate, we finally get only a few candidates. Therefore, we need a more intelligent, targeted way to explore the material space. Today, we generate the model to produce new entries especially using the generative AI. So we can use that technique to further accelerate this material discovery process. So considering this situation, we are I would like to talk about how what we are doing there, especially this structure property relationship of the quantum material discovery. Each materials have the structure, that atomic position, the unit cell, and atomic species. Different combination gives the different physical property. So we consider we use developed this methods for predicting this physical property using machine learning, as well as how we can, if we have some specific target material functionality, we consider how we can actually design that kind of material. That's we call the inverse design. That is the two pillars of our presentation. First, I would like to go into the talk about the property prediction. Especially in this talk, I would like to highlight our technique called the virtual node for predicting the phonon dispersion. Graph neural network is the method which is often used for representing the material structure. This convolution is come from the very conventional machine learning deep neural network techniques that convolve the pixel of the neighborhood to learn this positional relationship. And the graph neural network is to expand it to the graph architecture, connecting the nodes connecting the neighborhood node with the edge, and to do the convolution using doing the convolution in the similar way as normal convolution neural network. We can use this approach for the material that has initiated from the one MIT's group work in 2018 called the CZCNN. In administration, the node of the graph represent the atom in the crystal. Also, these edges, the connection between the nodes, often represent the interatomic interactions. In many cases, we connect the atoms of the neighborhood as the edges because it's on the top of the assumption that the neighbor atom affect more on each other, such as the overlap of the electronic orbital and also the interatomic the forces. In material case, they also consider this a periodic boundary condition, so that when we input this unit cell, that can fully consider the infinitely repeating the unit of the crystal unit cell. And also like the symmetry, like such as the equivariance, the method called the equivariant neural network can handle the rotation, some invariance, equivariance of the structure and the property relationship so that we don't need to augment a lot of the data. I feel that using the GNN approach, we have developed several models for predicting properties. One work is the magnetic ordering prediction using the GNN as the body model. We do the classification whether the input material have the non-magnetic ordering or the FM, AFM like that. Also, we also conducted this prediction of the optical properties. That is using our expanded method called ensemble, the universal ensemble embedding. Which enhances incorporate this atomic features more efficiently. We succeeded in predicting the optical spectra as a function of the energy axis. That could help us to identify this material that can be more efficient as the solar cell material candidates. As
I have
shown
a
here.
Question? Can you hear me?
Yes.
Yeah. So these predictions are these something like how are you training? Are you using some, I don't know, expensive simulation data? Are you using some simulation for calculation data to train? How are you going from what to property?
Yeah, it depends on what we want to predict. If we have the goal, like what we want to predict, and if there already exists the open source database, we appreciate this existing database. For example, like the left, the magnetic ordering, we trained on material data set called the Magnedata, which possesses some around 2000-ish some data of the experimental magnetic database.
But on the right-hand side, with optical properties, you're producing, I don't know, some spectra plots. So presumably those are based on simulation, some calculated.
Yeah. Right side is coming from the simulation data set.
So is the role of GNN interpolating between simulation results? Is that what you're getting out of the GNN?
So your question is there some difference between the experiment and simulation, you mean?
Yeah, I guess I'm trying to understand what do we gain by using GNN? So if for instance one modality would be one can do some calculation, but to do lots of calculation is expensive, so you train the model so that you don't have to calculate each time. Is that how your right-hand side is working?
Yeah, usually there is some ab initio calculation that can be the expensive, especially this material system become more complex, but this machine learning GNN based is more efficient. Scale is they can scale lighter than this conventional the physical simulation.
Maybe are you still introducing? Have you gotten to your main topic, or is this sort of a context and introduction? Maybe
it's more like the context introduction.
Okay. All right. Maybe you should get on to your main topic then.
I see.
Or I should get out of your way. Maybe that's the
Okay.
right.
Yeah. If you have any question, please feel free to interrupt me in the middle. Okay, yes, let me proceed. Actually, here, we talk about this GNN to represent the material structures, and so train it to output the target function, the property as the output. It's not limited to the magnetic ordering on optical spectra, but we can also expand to the other properties as long as we have the data set. For example, as we talked in the very beginning that the summer energy, summer energy management is also one of the interest in our group. Actually, from the one right the report we have seen that quite a bunch of the generated energy end up as a waste heat, even though that we couldn't make use of as electricity. To understand to understand what is happening and to find the new material to reduce these losses, we can use the GNN, especially the GNN for predicting the property or the physical properties called the phonon. Our group, previous group member has worked on this problem. We could find the phonon density of state as an output. We could do the prediction well. That with a high efficiency. This one is trained on this simulation data set. Using this phonon density of state, we can predict the physical properties like the heat capacity. This is still good, but it still have the limitation. Expanding the GNN capacity is to further know about this phonon. It's necessary to expand the capability of the GNN. Like in the previous slide, we talk about this phonon density state, but actually the phonon dispersion that's showing that the band structure is more informative. So it's essential to do the prediction of the phonon dispersion. However, compared to the phonon density state, the phonon band structure is more complex because depending on the material, this number of the spectra is different. That is can be written as 3 times the number of the units, atom per unit cell, as well as we also need to consider this dependence on this momentum vector. That we didn't need to consider in the phonon density state case. To solve the issue of the complexity in the phonon band structure, we propose a new method called virtual nodes GNN or VGNN. As I talked in the early slide, GNN represent this atomic structure by regarding this atom as one node and this interatomic interaction as the edge. Therefore, if you have this M atom per unit cell, we get this M output, in front of those cases, we aggregate this M output to get this graph level features. On top of that, we introduce the node called the virtual node. Virtual node represents a node, the atom, but it's the virtual atom that does not exist in the real world. We put this virtual atom into the GNN because even though they are virtual atom, but they work in the GNN so that they are depending on how many this virtual node we put, we can flexibly adjust the dimension of the output. Therefore, the phonon dispersion case, we can set the rule to adjust this number of the GN and the virtual node position. We can flexibly adjust adapt this GNN for phonon dispersion prediction. So in the following pages, I'd like to talk about how we did this phonon band prediction in the 3 stages, starting from the phonon at the gamma point, as also expanding to the phonon band structures, how we can incorporate the physics priors. The first stage is the direct prediction of the gamma phonon. We use the virtual node as the output gate of the GNN. Using the 3 times the number of the atom per unit cell as this output gate virtual node, we can get this 3 and values output. We can train this model so that the output from the virtual node is phonon as a gamma point. We can see that this prediction is working to some extent, even though we still have the room for improvement. The next one is the gamma phonon prediction, but it's more like the physics informed approaches. And actually, we use this virtual node to model this dynamical matrix that whose eigenvalue is the phonon frequency. We train this dynamical matrix version called the matrix virtual node to train that whose eigenvalue correspond to the phonon at the gamma point. This approach, because this is more like based on this underlying physics of the phonon, it's performed better than our previous the early version of the direct prediction. And furthermore, we do expand it to the full phonon prediction. That not only the gamma point, but also expanding to the prediction target across the whole Brillouin zone with a different momentum vector. It enables us to do the prediction of the band structure along the high symmetry paths. This again our purpose of modeling this material for property prediction is to achieve the high throughput screening of the material characterization in the efficient time and resources. Actually, we do the benchmarking with one of the existing methods called the machine learning in the atomic potential. One of them that is state of the art is called this MCGNet. We do compare the calculation speed of our VZNN and MCGNet. We could see that our VZNN is faster in the scale of some hundreds, several hundreds faster than machine learning in the atomic potential. Could see it for this trend for across the quite diverse materials.
Question.
Mhm.
So, I mean, I haven't spent enough time thinking about phonons.
Mhm.
What can you do by having all this information about phonon? What kind of prediction can you make?
What kind of
If I know everything I can know about phonons, what prediction can I make with it? What kind of property can I predict with that?
I see. I think that I think there are so many. If I remember, correctly, the heat capacity, thermal conductivity, and also the interfacial transmission of this thermal energy. There's all related, and also this one doesn't have here that we do the prediction of the harmonic phonon, but the other more future work is we expand to the more harmonic phonon cases. We can also consider as coefficient of the thermal expansion as well.
Mm-hmm. But can you also get spectral function? You still cannot get phonon spectral function with having all the dispersion and everything does not give you the phonon spectral function, right?
Yeah, it's not directly giving the distance.
So you cannot use this to make sort of a detailed prediction for phonon-mediated superconductivity, for instance.
It's right. That's still the limitation. That we can consider how we can expand our the phonon prediction modes to the more the further application, including this electron phonon coupling stuff. But it still has the room for improvement and some further application. There are many possible further applications by expanding the model.
Is this something that you guys have thought about but have limited performance, or is there a sort of fundamental challenge within this approach to get alpha square F?
Could you say again? I couldn't hear what you
To
said.
get phonon information to do, for instance, Eliashberg theory for superconductivity.
Mhm.
If I want to predict phonon so that I can predict electron phonon, phonon mediated superconductivity,
Mhm.
like what you're showing us at the moment are not the properties that I can use to make prediction, right?
Yeah,
So
right.
my question is, with your framework, have you guys tried to make predictions, for instance, for phonon spectral function or phonon alpha square F for Eliashberg theory? Have you guys tried, or is it something that you haven't tried yet?
The short answer is we haven't tried.
Okay.
Yeah.
So what you are getting out of this is dispersion, phonon dispersion, and the density of states. Dispersion will give you the density of state. So phonon dispersion is what you're getting.
Yeah, phonon
Phonon
dispersion.
band.
Yeah,
Okay. All right. Thank you.
thank you. Yeah, like, if you have any other question, please let me know. Otherwise, let me continue. Yeah, like we have worked on this the photon prediction. VZNN is like not only that for the periodic crystal, but also like our system is also the target. Like we represent that is the atomic species by calling the method like the vector called the one-hot vector that the atom like of the specific the atomic number have the non-zero element on this like the specific this the vector position because it is the silicon has that is the non-zero this usually is the mass of the this silicon other value of the index of the this silicon atomic number same as the germanium in this case the silicon germanium. When we consider it to represent this alloy we can like do the array representation like in other words it's we call that the machine learning Barger crystal that is mimicking this with the approximation. By using this approach like we can like see that the tendency similar the phonon prediction of the silicon germanium alloy show the similar tendency of this ground truth. See that as the more that the ratio of the silicon increases, the higher this the phonon dispersion, this the bond structure, like the phonon energy, this the range becomes. Yeah, so far like we have talked about this phonon dispersion prediction can be like achieved by this Barjanol's capability to expand this limitation of the dimension. Okay, so this is so far the first topic we have discussed about this prediction of the physical property, and the next part is more like this inverse design of the materials using the generative AI. Like here in the previous chapter we talk about like the property prediction for this high throughput screening and this material characterization. However, like that as like in the recent like the tens of years, this generative AI approach has becoming the majority, this dominant part of this material discovery in AI. You can see from this figure I extracted from one of our recent review article showing that the ratio of the material discovery papers using this inverse design has get larger and larger as there emerges a different the generative AI techniques starting from the VAE and GN and also like the diffusion model and even the language model. Especially amongst them, like we can see that
Question.
okay,
Question. Can you go back to your previous slide?
this one.
So the vertical axis is number of publications.
Uh-huh.
Number of publications is not necessarily, I mean, I don't know what fraction of those publications actually report new material. People can write papers, but writing papers does not define productivity, right?
Mhm.
So what fraction of those papers actually are reporting discovery of material?
Discovery of
Is there a data for that? Yeah.
I haven't actually checked how many of them are related to the material discovery, but my guess is it's quite low. Like this paper, like we talk about is the ratio of uh like the computational is the material discovery framework, but most of the papers, including some machine learning conference papers, like they're more focused on the methodology of the computational technique. Many of them doesn't like highlight the actual our ultimate goal of the finding the new materials. So yeah, we think that this ratio of the actually finding the new material is quite low.
Okay, thank you.
Oh, yeah, like one of the emerging like the technique for the generative model is called the diffusion model. That is, they often used in the image generation. The model learns that this from starting from this pristine nice realistic image, it adds this noise iteratively until it become the completely random this noisy image. And this diffusion model learn how to reconstruct the original image from starting from this diffusion the noisy image. What we call is it learn the pathway to denoise this image iteratively by predicting this denoising time. That enables starting from the noisy image and generate a realistic image. This is a case of this image generation, but we can do this approach for this generative model for this material. If we break down this problem, this material discovery, it's actually this numerical problem that is a joint optimization of the three components, L, F, and A. L is a unit cell shape that can be one time we can also represent is a 6 lattice parameter that is the unit cell the parameter is the length of the ABC and this the lattice angle alpha, beta, gamma, and this the atomic coordinate where this each atom are located, and also the atomic type n. This the L and F, this the lattice and coordinates are the continuous value, but this atomic types is a discrete value because each of them need to represent this represent the atomic species that can be can be written as this atomic number. By doing this on top of this assumption, we can do this diffusion model that it starting from the randomly initialized component, optimize this three component step by step. As we can see in this bottom movie, we can suggest that this material structure that has a realistic appearance. The realistic means that the atom the positions are not too far or not too close to each other, and the combination of the elements are realistic in terms of some repulsion or this charge neutrality. There have been emerging the many papers doing this crystal structure prediction (CSP) that giving the chemical composition to predict what the actual realizable phase crystal structure phase is like, and also even the de novo generation completely starting from this random the structure. Not only just the unit cell and coordinate, it's also we can also do the prediction of the chemical species. I mean, this de novo generation is more like the higher degree of freedom. This the bottom row, we show that is the CDVAE, the crystal diffusion variation autoencoder. That is a very pioneering work of this crystal structure generative model, as well as the DCSP. That is the more advanced version of this crystal structure generation, which we are heavily relying on. There has emerged many techniques. This one review paper shows a bunch of the techniques for doing the material generation, including covering the many the machine learning and generative model approaches, starting from not only the diffusion model, but also there have been some technique using the language model. Among a bunch of the papers for this material generation model, conditional generation is becoming the mainstream of the material discovery. It is proposed material structures condition on the target property. For example, the Microsoft Multigen generate materials conditioned on the space group symmetries and even the scalar properties like the band gap or the bulk modules. This shifts to the conditional generation. We generate this explore the material structure that have the certain property has been the mainstream of this desire to find this material of the desired property. However, there still remain the challenges in this conditional generative approaches. especially in the quantum material communities. The issue is that only a few, like the limited portion of the material present some interesting this quantum phenomena. Therefore, the number of the candidates which we can train on this quantum material is quite limited. For example, in the quantum the material community, the geometric motif is said to be some one like the common sense to present this exotic phenomena that is cannot be fully explained that cannot be fully tackled by the existing conditional generation like the matter gen. For instance, like the Kagome lattice that's I show in the left plane can we give rise to this flat band structure, which are important for like the many strongly correlated systems. Also, like the magnetic atoms, like that sit on this some geometries like the triangle lattice and honeycomb and this Kagome lattice can introduce this magnetic frustration, which can potentially lead to this quantum spin liquid candidates. Today, there are only a limited number of this material, so it's not realistic to train the fine-tune existing generative model with this quantum material candidate. Therefore, we need to expand the regime of the existing material candidate. Again, like the geometric constraint, like what kind of motifs to possess can be the key for this quantum material discovery. So we raise the question. Could we generate these new materials by imposing the target geometric motif as a prior or as a constraint? For example, like having this magnetic atom, like the magnetic or the metal atom on this corner or this triangular side honeycomb and this Kagome. So we can guide this generative model by this structure constraint. To address this issue, we conceptualize the SciGen, the structure constraint integration in generative model, as a new method to impose this geometric constraint into diffusion-based generative model. In the very briefly, we make sure that the presence of a specific geometric motif, for example, like the Kagome pattern, should definitely appear during this generation. We allow this unconstrained part of the crystal. Unconstrained means that the atom that is outside or different, forms the other part, or the part other than this Kagome lattice part. Finally, we combine this constrained and unconstrained region to form the full material. This process enables us to design their stable, physically meaningful crystal structures with embedding the target patterns. In the next slide, few slides, I will go into a little bit more details of this algorithm. This is show the algorithm background of this SciGen. It's like as in the similar way as this image generation, we do this denoising of the crystal structure iteratively, but in this process, we combine this structure constraint of this target structure motif like Kagome. Initial part start from it start from giving this initial target structure motif. That is what kind of the structure, geometric pattern we want to impose to the crystal. For example, we can pick what kind of this geometry, such as triangular, honeycomb, and Kagome, and also we can pick up what kind of the atom you want to sit in this side, as well as how many atom or what the bond length is. That is a starting point of this generative model. In the later stage, we consider how we can actually impose this constraint in this to guide this material generation. And the next step is to initialize this crystal structure. As we showed in this image generation part, which start from the completely noisy image, we initialize this very random this crystal structure. We initialize this the noisy step. Underneath the later part, for each we repeat this the denoising step that is coming from starting from here. Before doing the denoising, we sample the structure of the certain time step with the superscript C. C means the constraint part. This part. Since in the very beginning we prepare the target structure motif, we can intentionally add the Gaussian noise to this structure, the structure motifs, so that we can provide the pathway, guiding pathway, so that we can guide the other part of the crystal to fit into the rest of the structure motif part. The later part, we sample this unconstrained part of the structure. This part, we use the GNN, so that given that this current structure, the noisy structure, that outputs the term that can give the less noisy structure. In this case, inputting the noisy some structure as a specific time t, outputting the unconstrained part of this crystal structure. By repeating by accessing this constrained and unconstrained part of the structure, we combine these two components by using the mask, where that distinguish the constrained and unconstrained part. That is, we have the constraint and unconstrained part. For each the lattice and the coordinate and the atom, we combine the two components together to get this integrated structure. Then we repeat this process, the initial sample, the constraint and constraint component, and combine together. This repeated iteratively, usually 1,000 times, and that give us the crystal, the structure. That can give us the structure that definitely helps the target structure motif, but it can guarantee that this can gain the stability by a high chance. However, at this point, that as we impose the human intentionally impose this structure motif, some situation it can be not realistic. So after we generate a bunch of the material, we need to do this high super screening, which we set up in this work. For example, the charge neutrality, atomic species occupancies. It means that the atoms shouldn't be packed to the null species, and also energy above complex 4. And as an optional, we also incorporate since we use a diffusion model, many of this generated material looks at some diffuse from this high symmetric side. So we limited the material that looks like the very diffuse structures. This image, this movie shows that how the structures are optimized. Starting from the noisy crystal structure, it imposed to have this geometric pattern, like the triangular honeycomb and kagome, and also I showed this square lattice. It's guaranteed to possess this kind of this target structure as a part of this crystal.
Question? So
Mhm.
is your goal to find, let's say for Kagome, is your goal to find new material with the Kagome motif? Is that the goal?
Yeah, actually, it's our ultimate goal. If you don't have this generative approach, all we can do is to start from the existing database and screen out
Right.
the material with the Kagome, but
Right.
could be
So
limited.
okay, so that's a great goal. Did you succeed?
Actually, it's not the exact match, but inspired by the result of the generative model, we could collaborate with experimental team to find out that is the synthesizable materials, which I'm going to talk a bit in the later part.
Okay.
Okay, so let me continue. we could generate this material candidate by importing this target motif. Here's some example of what we could see using three primary types of the Archimedean lattices, that is the triangular and honeycomb and cogomate lattices. We could see that the magnetic or metallic atoms sit on this side of the target motif, and other atoms are trying to sit on the side to stabilize the target structure motif. For we can see the material such as for example, the iron oxide, the triangular atom, that is that the iron sit on this triangular corner, and this oxygen is trying to sit on this around the center of this triangular on this different plane. And we can see the similar, like the kagome, to stabilize this kagome structure. Like we can see the other atoms sit on this center of this hexagon, as well as this on this center of this triangular part of this different plane. We can further expand this Archimedes structure motif to the more different diverse kind of the structure we call the Archimedean lattice. Starting from the very simple square lattice, we can also consider the geometric pattern of the combination of a triangle or the square is hexagon, etc. We can for each candidate which could see this material structure that could pass this pre-screening by this high throughput the property prediction, as well as we conducted the DFT structure representation for subset of this generated material. And also we could see the subset of material could present the part of the material to be stable. After the large part of this material could be stable after screening out by pre high throughput screening.
Question?
Mhm.
So, after getting the results of the DFT, like, would it be possible to feed that back into the generative model to like augment the data that you're working with, or can you foresee some sort of like feedback mechanism?
In this work, we haven't incorporated, but yes, we can definitely work on that. We generate the material, run the DFT, and find that it's a stable candidate. We can incorporate this, generate a stable material as a further training data set. We can run the feedback, on the fly loop, so that we can generate some more. We can make this generative model more expert in this generating this strong material with this target motif. But there could also be a risk that if we conclude this feedback group within our existing data set and generate the material, there could be the risk that the material output material could be more biased to some specific regime.
Mhm.
Okay.
Oh, thank you. You can continue.
Any more question?
No, you can continue.
Okay, thanks. Beyond this Archimedean lattice, we also worked on the leaf-like lattice. That is the leaf lattice is the square lattice where both the corner and the edge possesses this atom. The geometry of the leaf lattice is reported to possess the magnetic frustration. Main interacting spins are placed at each lattice side. In addition, there is a report well known that the leaf lattice the material can lead to the unique electronic properties such as flat band structure. To investigate if there is any similar material of this similar nature, we run the DFT for the band structure calculation for this subset of the leaf lattice. We could find materials that show the flat band structure near the family level as this target from the generated material. And also, we include this new method called this the adaptive unmasking. That is like the technique to balance this constraint we impose and this the more realizability of the crystal structure. That is like in the previous page that we showed this lib lattice that is this square on this square plane. This the atom at the corner and this the atom on the center are on the same plane. But in the actual real world experiment, there is less chance that there is a higher chance that all the atoms are exactly on the same plane. There could be more some distortion or the variation that the atoms can be on or above or below the plane. And also we can consider the case that there are the atoms forming the Lib lattice site could be not only a single type of atom, but could be the multiple types of atom, which we call this hetero atomic Lib lattices. Actually, it is inspired by let's say, the analog of the cuprate and the nickel superconductor. So we aim that by using some heteroatomic Lib lattices, by using the adaptive unmasking, we aim that this framework could they provide this new material candidate replacing this existing superconductors. So far, we could see the material such as BT or the lithium mangan oxide as this generated material. But yeah,
Question.
yeah.
I mean, it would be nice to have more, say, Lib lattice or Kagome lattice materials,
Mhm.
but there are already many such materials. But often, problem is even if you can have flat band somewhere because of the motif, the chemical potential is not where the flat band is.
Mhm.
So having the flat band does not impact the electronic properties.
Mhm.
That's the problem with many existing materials with interesting lattice motifs. So can you predict where chemical potential will be? Like, can you figure out how to, like, among your desired properties, if you can peg the chemical potential where you want, like near the flat band, then you will probably get something really interesting.
You mean that is it close to the flat band, close to the Fermi level?
Most of the materials have flat band far, far away from the Fermi
Yeah.
level.
Yeah.
Doesn't matter.
Mhm.
So can you make having the Fermi level at the flat band be one of your desired outcomes that you're conditioning upon?
Yeah, actually, that's very good question. Thank you so much. So far we haven't realized that, although we are interested. Some challenge we need to overcome is how we can quantify or what kind of the descriptor we can use to quantify the presence of the flat band structure near the Fermi level. Compared to the form dispersion, which we showed in the previous slide, the electronic band structure is more harder to incorporate into the machine learning because formal band structure we know that it's the 3 times the number of the inner cell as this number of the band. But in this electronic band structure, we need to consider the number of the orbital, how many orbitals to consider, etc. And that is not, we haven't set out the way to universally represent for diverse different material. In that situation, we will need to consider how in the easy way to quantify let's say flatness near the band flatness near the Fermi level. Once we could quantify it, or represent it, we can use some conditional generation. We can combine the structure aware the generative model with the property guided generative model.
So that's interesting because when human looks at band structure, very quickly they can say,
Yeah.
there's my flat band and there's my Fermi level, right?
Yeah.
But we don't know how to give that to machine. That's what you're saying.
Yeah, something like that. Easy, some intuitive way is using giving the band structure as the image and quantify,
Right.
using some image processing model to identify
Yeah.
the presence of the flat band side. Well, yeah,
Mm.
that could be the one way, but we haven't tried that. I naively thought of whether we can use this electronic density of state that is more easier than the band structure to use the EDOS for identifying uh, flat band structure near the Fermi level. I assume that if you could find some flat peak around the Fermi level, I thought that could be the indicator. However, like that, in many scenario, the importance of the flat band near the Fermi level, like the flat band doesn't need to be the whole across the Brillouin zone. So density of state can tell something but does not tell all. So yeah,
Yeah.
to guide the material for the flat band near the Fermi level, yeah, we need to consider how we can represent
Mhm.
quantify or represent the band flatness in near the Fermi level in some easier way to incorporate into the generative model.
Okay, thank you.
Yeah, so far this is for the Lieb lattice-like material for some material finding that there's a flat band material candidate. But yeah, we have seen that the heteroatomic Lieb lattice is coming from the magnetic atom plus the oxygen. Furthermore, we did some property classification model to screen whether this generated material is magnetic or non-magnetic. For this across this for each table, we see this rows show what kind of element we impose as the geometric the motif, and this horizontal is what kind of the geometric pattern, triangle, honeycomb, and kagome, etc. For this across this different structure motif, we could see that the material with a specific atomic types such as mangan, the iron and gadolinium tend to present the more magnetic material. That tendency is not exactly the same, but very similar to what we see in this material project. Okay. Now finally, we could see that generative material. We could run quite a bunch of these numbers of this material generation to around 10 millions. Among this subset of the material, we run this DFT after pre-screening. We could do among this 26 K material which we run DFT, more than 24K materials converge, and more than half, around 6% of this material which run the DFT was verified to be stable. We could compare this into this data set and put it into this supplementary material, the paper, as well as this Figshare, this data set. And this among this generated material, we use some inspired by this generated material. We collaborated with the experimental team to do the material synthesis. We have seen that even though the structure is not exactly the same, we cannot deal with the material of the fractional, fractional, some probabilistic fraction of the atomic species. So we cannot do the model everything, but we could see that the experimental some results show that it's the similar or the relevant material structure, and these two material presented magnetism. One is paramagnetism, another is the diamagnetism. And this result suggests that the SciGen can discover the meaningful competing phases of the known materials. Okay, so to summarize, our structure constraint integration generative model has enabled this generation of the material with the arbitrary geometric motifs, including kagome and honeycomb. However, this the motif alone are not enough, as one of this audience asked about this flat bar near the Fermi level. Future approach should consider how we can incorporate this geometric constraint with the property targeted generation. Actually, this geometric this motifs is important. Let's say the carbon lattice with the magnetic atom could be important for finding this interesting magnetic material, but the other some filler atoms that sit on the center or on the different plane of this crystal can take the important role that can interfere with this orbital of the Kagome lattice as well. So we cannot tell everything from this this geometric motif. Therefore, on top of this the structure-based material generation guidance, we should combine this property-based material structure guidance. By combining either one or the multimodal properties, we expect to expand this domain knowledge on this existing accessible material candidates. That can potentially lead to the more expansion of the material database and lead to for the enhancement of this AI for material, as well as actually this physics problem, both the computation and experimentaries to work on this new system. Okay, so this is all of my presentation. Thank you so much for your attendance. If you have the further question, any other more potential collaboration, further discussion, I'm very happy to talk with you. Okay, thank you so much.
Thank you so much for the excellent talk. Any questions?
I have a comment.
Oh, comment. Yeah, we love comments.
So first, this will sound negative, but I very much enjoyed the talk. And there's a sense in which this work is complementary to the kind of work in machine learning that was done with AlphaFold to predict the properties of proteins. And this brings it into the material science realm. The comment I was going to make may strike you as a little odd. It just occurred to me that the name SciGen was previously used about 20 years ago in a context which is kind of amusing in the light of Eunha's sort of deadpan cynicism about people writing lots of papers but not necessarily doing anything, which is that SciGen was developed at MIT, and it was a program that generated fake papers. So you should look up the history of the use of the term SciGen. I understand you're using it because you have generative models of materials, but they had a generative models of papers using probabilistic context-free grammars. And I don't know if you want to avoid the name collision or if it's too late.
Thank you for I already seen the SciGen name, but I think that it's alright because the spell is different. The objective of this work is in the difference, so it should be I already talked about this the presence of the other some the name or the method, the program with a similar name, the spell, but with advisor, but should be not be their problem so far. Thank you so much for.
I understand you're saying I'm the only one who might be confused.
Okay, thank you so much for your advice.
Any other questions or remarks for our speaker? If not, let's thank our speaker again. Okay. Thank you so much for the talk. Appreciate your time.
Okay, thank you so much.
Yeah.